All right. Electricity, magnetism, and electromagnetics, and this is chapters, like I think 6 and 7 in this current edition of the textbook. I'll double check that here. So here's my learning objectives. We want to look at how magnetism relates to X-ray production and the detection of X-ray. So our chapter does a good job. He does a good work of pointing out that both in terms of producing X-rays and then also detecting radiation, we can use magnets or magnetic fields, right? We're going to talk about the 5 laws of electrostatics. That's basically electricity at rest, and that's when we'll look at John's voltage, right? And interestingly enough, this is related to the inverse square law. So there it is again, our old friend, right? We'll talk about how objects become electrified, and can you become electrified, and what would happen to you if you did. So we'll talk about electrical current, which we've already alluded to here as being related to the production of electrons needed for X-rays. So we are going to be talking about mass and how to calculate mass. And we've got some electrical circuitry stuff. And then we're going to illustrate electrical power. So we'll be talking about calculate the effects of various circuits on electrical current and voltage. All right, good. Oh, sorry. Good. Those are the objectives. So magnets. Magnets are not miracles, right? They do not fit within philosopher David Hume's definition of miracles. But the science is like stupid deep on these things. So the main thing to remember about them is all moving electric charges develop magnetic field lines. And they kind of emanate in concentric circles off of those charges, right? And number 2, you're a waste of carbon if you dig the Insane Clown Posse. That is not in the book, but it probably should be in the book. All right, so where are these magnets going to be for us? Well, first off, within the X-ray tube, we've got a magnetic field potential that we are exploiting with the production of electrons and accelerating them towards a positively charged target, right? So we've got negative charge on one side. Paula Abdul taught us that opposites attract. And so, therefore, that's what's going to happen between the electrons and the positively charged anode, right? The other way that we will use magnets is going to be in an electroscope, right? And we don't really use electroscopes anymore. But if you are interested in ways to detect X-rays, a way that something that's developed out of the electroscope is the pocket ion chamber. This is on page 112, right? And what it does is it uses electrical charge produced by ionization as a measure of detecting X radiation, right? So as these 2 leaves here become increasingly ionized, they both develop a negative charge. Those negative charges repulse each other. And so we can measure the amount of ionization relative to how far apart these metal leaves have moved from each other, right? Because as they're more and more ionized, they're developing more and more of a negative charge, and they are repulsing each other that much more. So just like if you take 2 magnets and you try to hold them together, like to like, they repulse each other. Same thing's going on. And this is a lot of the foundation of X-ray detection, right? Or radiation detection, the detection of ionization. So yeah, those are the big things with magnetics. Now, the textbook gets into a lot of stuff related to spin, right? Magnetic moment, what's going on inside of dipoles and atoms and compasses next to electrical wires. Is that stuff important? Yes, it is. It's really important. I don't really care about it that much right now, right? And it's not because I'm lazy. It's because you're going to get 2 semesters of it when you take Mrs. Smith's MRI class, right? So I don't really feel like like beating the dead horse when it comes to this stuff. So I'm not going to ask you as many questions about like net magnetic moment or any of this other stuff that frankly was probably developed at Area 51. That will come later. But what I am interested in is static electricity. We do need to understand this right now because this is an amazingly awesome thing to do to your cat, and I think everyone should, right? I do not like cats, and you'll learn that about me. To do this to a cat and to understand how we're going to use this for x-rays, we need to understand the 5 laws of electrostatics, and this is dealt with in our textbook on page 107. It's important stuff, right? So if you're wondering, how does this relate to, so I've mentioned that ionization of atoms is occurring anytime we've got radiation interacting with atoms, right? And we can understand this electrical charge that's occurring inside the atom as a measurement of the amount of ionization that occurred. And so what we have here on page 107 on this paragraph right here is the unit for electrical charge is the coulomb. This is named after a pioneer in the study of electrostatics. 1 coulomb of negative charge represents 6.3 times 10 to the 18 electrons. That's like a billion, like a gugazillion electrons, right? So 1 coulomb is a ton of electrons, right? So when you are in the wintertime and you're trying to pump gas or whatever, and you got sparks jumping from your fingertips to the gas pump and blowing up the gas pump or whatever, this is only a microcoulomb of charge. But I don't know, I lived out west for a while, and if it got cold enough and you've got a good static charge going on, and you touch your like doorknob when you're waking up in the morning, it can nearly knock you across the room, right? So these electrostatic charges can release a tremendous amount of energy, right? But what's interesting about this is this coulomb is going to become a major way that we will measure radiation dose. It's going to become tied to how we're measuring ionization. Okay? So file it away in the back of your mind. Also understand that it's going to allow us to calculate roughly how many x-rays we're producing, right? So we're going to be able to use this number. We're going to come back to this number, so I would highlight this paragraph of 6.3 times 10 to the 18 electrons in 1 coulomb. We're going to highlight that number. It's important, because if we know that gugazillion huge number, we can calculate how many x-rays we've produced when we energize the tube, and it's a lot. Like it's a lot. But kind of looking down to the next paragraph, here's our 5 laws of electrostatics. Like charges repel, unlike charges attract, opposites attract. Only the electrons are moving. So when I touch that doorknob and I'm shocked across the room, I am not moving atoms, I am not moving neutrons, I'm not moving protons, I'm not moving some subatomic particle, I am moving electrons. That's important to know. I'm just moving a negative charge. Electric charge distribution is uniform throughout or on a surface. And this goes back to the first 2 things. So when we look at John Travolta's here in a minute, the game is this. You scuff John Travolta's feet on the carpet, he starts to develop electrons through the static electricity in his foot. And those electrons start to distribute throughout the entire surface of his skin, which is exactly what happens in our skin when we wake up in the morning and it's cold outside. The electrons are evenly distributed throughout the entire surface. Why? Because electrons repel each other. So if you're developing trillions of these things across the surface of your skin, they are all repelling each other, right? So they're evenly distributed across the surface, right? The charge is going to concentrate upon the sharpest curve of a conductor. So if something's capable of conducting a charge, the charge is going to concentrate here on a curve, right? Which is really interesting if you think about it. And that's going to be why we're going to use curves over here, like on our filaments and on our stators and stuff, as a way to develop that charge, right? So the curving of wires is going to be really important. It's going to be a critical part of how we work with these things. And then finally, electrostatic force is directly proportional to the product of electrostatic charge and inversely proportional to the square of the distance between them. What does that sound like? Inverse square law. It happened again. I know. Science. And not having a schizophrenic breakdown. It does all relate. So here it is, inverse square law, applying now to electrostatic force, right? So let's pause the lecture now. Okay, the only thing that I'll add to our discussion of electrostatics, right, is on page 108 and 109 in our textbook. Objects can become electrified in 3 different ways. By friction, and that was John Travolta scuffing his foot over the carpet, right? By contact, that's him touching the doorknob, and then by induction, right? And an inducted charge is one that's moving from one wire to the next. All right? So let me see if there's anything I would add to that. And one thing maybe to add to induction, on page 109 where it talks about induction. Electrification by induction occurs when a charged object induces a charge in another object without directly touching it. So without directly touching it. So maybe it's helpful to think about it this way. If we go back to John Travoltage, we got friction scuffing the foot on the thing, right? The next one is moving down here. Sorry, contact, right? Him actually touching the doorknob, right? And then induction, him getting his finger pretty close to the doorknob but not actually touching it, right? So we can conduct electricity in those. We can cause electrification in those 3 ways. Okay, so again, if we have a garden hose, right, and we've got increased pressure, what just happened? We would expect for increased flow of water. So increased pressure would equal increased water flow, right? In a compared statement, if I have increased voltage, I would expect to see increased current. Oh my Lord. Why is this happening? Decreased voltage, I would expect to see decreased current. Right? So the same thing as turning the water on and off in a garden hose, right? That is what we're dealing with when we deal with electromagnetics. So we've got conductivity, the ability for electricity to pass through a substance, right? It passes through certain metals better than others, right? Some things simply don't conduct at all. So silver, aluminum, brass, and several other metals, including water, allow electricity to pass through them easily and are called conductors, right? The potential difference in that system, in that conductive surface, as it passes through it, we will call the voltage present, right? And then finally, the flow of the electrons through that conductor is what we're talking about when we talk about current. Let's look at it like this. So here we have 2 different systems, but we're drawing the analogy further. So we're saying the pump is like a battery, right? The battery gives some amount of volume or flow rate, in this case voltage. It's applying that potential difference down the wire. As that's indicated, I believe in this diagram by the I. Let me double check that real quick. Yeah. Oh, I'm sorry. Oh. I is the amperage in this case. So the amperage is the amount of flow that's occurring in that wire, right? The I is the amount of flow. So in the related diagram, it's the arrow with the F by it, right? When we get to the resistance, you can think about that as a stricture, or like a place where the water narrows, right? Like him crimping off the hose. That would be resistance, right? Generally, we symbolize that with this squiggly thing that looks like Charlie Brown's sweater, right? That stands for resistor, right? So you can see on the side opposite the resistor, right, we've got a reduced amount. In this case, 0 voltage, very, very reduced amount of amperage, right? So we've got a low voltage on that side opposite the resistor. And down at the bottom, it's got an expression of Ohm's law, right? And this is found on page 119 in our textbook, as well as some problems asking us to solve for different things in Ohm's law, right? I like this table here as well in our textbook, the characteristics of electricity. Current is expressed in amperage, can be abbreviated I or A, right? That potential difference or electromotive force is going to be in volts, and it's generally abbreviated V. And then resistance is expressed in ohms, and it's got the weird omega sign. So if I am wondering in the back of my mind why all this matters, right? It all goes back to the X-ray tube, right? That's why I need to know about this stuff. Because current, I've already said current and electrons are the same basic thing. So through the garden hose, we have water molecules flowing. In the X-ray tube, we're creating a flow of electrons, right? And that rate of flow, or that current, is the amperage, and it is directly related to the intensity or the quantity of X-rays being produced. The intensity or the quantity of X-rays being produced, right? Interestingly enough, we can relate this back to the Coulomb, right? Which I said earlier was that electrostatic measurement, right? And so in this case, 1 amp equals 1 Coulomb per second, which equals 6.3 times 10 to the 18 electrons. So if you know the mass, right? If you know the mass that's been set in the in the X-ray tube, you know the number of electrons that are being produced, and you know, and you have an idea of how many X-rays have been made, right? So again, that's what I mean when I say quantity. So in case you didn't miss it, because this is something we'll repeat over and over and over again, and it's something that took me a long time to make sense of, intensity equals quantity. Intensity equals quantity. All right. So I don't necessarily want us to get bogged down in the weeds of Ohm's law and all that stuff, although we are going to look at Ohm's law and we will do some formulas and some problems related to Ohm's law. But really, the primary reason that I'm interested in mass is because I use it every day as an X-ray tech, as a CT tech. I apply it to all sorts of patient care situations. I'm constantly messing with the mass as a way of changing the technique and the intensity of the technique to accommodate different patient sizes, different pathological conditions, different constraints within the X-ray room, or if I'm working portably within the portable room. So it has a lot of practical applications. All right. The other thing that we need to understand from an electrodynamics point of view is we need to be comfortable with these symbols here. So I've already mentioned that we got Charlie Brown's sweater there. That's the resistor, right? We got this weird looking thing that they say is a battery. You know, electrical engineers clearly didn't take any art lessons, but a capacitor. And believe it or not, you are a capacitor, right? The human body has the ability to store electrical charges, right? If you're interested in other examples of capacitors, a taser is a capacitor, right? It has the ability to store a charge, and if it's touched to your body, since you have the ability to store a charge as well, that charge moves very rapidly from the capacitor to your body, right? And it hurts. The one that we're going to probably work with the most, or the two I should say that we'll work with the most, are transformers and diodes, right? We're going to do a lot of stuff with transformers. So I'm going ahead and introducing them now. We'll be talking about them more when we get to the X-ray circuit. But know that that symbol there represents a transformer, and it's working off of the principle of induction. So I said that this is a way that we can electrify things, right? So this is, in essence, a drawing of John Travolta's finger as it approaches but doesn't actually touch the doorknob, right? The finger gets very close to the doorknob. It never actually touches it. There's an induced charge that passes between them, right? So transformers do a lot of work, not just change from cars into robots. That's important work for them to do as well. But the main thing they're going to do in our X-ray tube is allow us to vary the voltage and vary the current from one side to the other of the transformer. Finally is the diode. And this allows electrons to flow in only one direction. Now, what's interesting about a diode is that within a diode, it has an anode and a cathode. So in essence, an X-ray tube is a gigantic diode, right? But we will use them to control the flow of power within the X-ray tube. So I want us to be familiar with these symbols, transformer and diode being the most important. All right, let's talk about series and parallel circuits. I find this stuff pretty boring. In terms of electrical stuff, this is the least entertaining of it all. This is the old Christmas light analogy. We do need to know a little bit about this, and if I'm frank, if I'm completely honest with you, this is just stuff you need to know just to know. It's not necessarily that applicable to our work. It's just still part of the test. So the rules for series circuits is the total resistance is equal to the sum of the individual resistance. The current through each circuit element is the same and equal to the total circuit current, and the sum of the voltages across the current element is equal to the total circuit voltage. This is like the Christmas lights that if one bulb goes out, the whole string of lights goes out, right? And you ask, why is that the case? Is because the total resistance is equal to the sum of the individual resistances. So if I have a bulb go out, there's no current now flowing through that bulb, and so all other bulbs go out. All right. Comparing that with the parallel circuit, this is pretty much every Christmas light that you've ever had, right? Because almost all of them are made now in parallel, so that if one bulb goes out, the rest of the bulbs still stay on, right? So those are in parallel. So the sum of the currents through the total circuit is equal to the total circuit current, right? And the voltage across the element is the same or equal to the total circuit current. And the total resistance is the inverse sum of the reciprocals of each individual resistance. I don't care if you know that. Let me tell you that straight up. If you understand that this one is like the Christmas lights that don't go out, and the other one is like the Christmas lights that do go out, you're good to go, right? So we only need to know what Mr. Wolf calls this kind of Fisher-Price level of understanding of this electrical stuff. I'm not an electrical engineer, and I don't expect you to be, right? But what do you need to know? You need to know what will keep you safe and what will help you take good x-rays. So this stuff is just, I don't want you to get bogged down in thinking about x-ray circuitry. We're going to represent the x-ray circuit when we get to it in a few weeks as a very simplified process, right? But recognize that most of it's happening in parallel, and it's fairly complex if we were actually to do the wiring. Now it is helpful to understand these symbols and to not get distressed if we see these symbols like things like batteries, resistors, switches, transformers, and things like that. So being comfortable with these kinds of schematics that I just showed you is helpful, And I don't want you to be freaked out by them. Be comfortable with them. Know that you only need to know what you need to know to keep you safe and keep your patients receiving quality care. But let's look at Ohm's law, because it is going to be helpful to us to be able to calculate these different resistances and to be able to understand what's occurring, right? So here we've got a similar garden hose situation, right? But what we're doing is, rather than just have the water flow out of a spigot on the side of a house, imagine we've got this water tower, right? So we're back at the marbles on top of the whiteboard analogy, right? Now we've got this water tower. The higher up I make the tower, right, and the more and more water I put in the tower, I've got more and more potential, right? That's an increased voltage. I've raised the tower up higher, I've put more water in the tower. It's like raising the whiteboard higher and higher. I've created more and more potential energy there, right? The current is going to be what happens when I open up that system and the water starts to flow through the hose, right? So if I did not have the tower very high, I would not expect the current to flow very quickly, right? So if I don't have a huge potential difference, if I don't have a huge voltage, I would not expect there to be much amperage, right? Conversely, if I have a lot of voltage, I would expect the amperage to increase as well, the amount of flow to increase as well, right? This is precisely what we are using to bang the rocks together, as it were, inside the X-ray tube. We're increasing the voltage a lot, right? And we're allowing more and more electrons to be fired across the inside of the tube, right? So we're increasing the kVp a lot, that kilovoltage peak, we're increasing it a lot, and we are allowing that to suck more and more electrons across the distance. So that's the name of the game inside the X-ray tube, is just this formula here. We're not going to worry too much about resistance, because inside the X-ray tube, we've got a freaking vacuum, right? Vacuums are your friend. So we just got rid of resistance altogether. So now we have this huge amount of potential in the kilovoltage range, right? And we're boiling off these gigabillions of electrons and accelerating them across a space with no resistance, right? So this formula is telling me why, when I bang these tiny rocks together inside of an X-ray tube, I'm producing so much energy, right? Because of this situation here. Okay. So let's talk a little bit about Faraday. I mentioned him in the last lecture as someone who created the science that allowed for the discovery of X-ray. And the science that he worked on was electromagnetic induction, right? He was very interested in how to induce different types of current, right? How to produce more current. And so that is very helpful for us. And what he said is that the size of the induced current, right? And this is John Travolta's finger getting close to the doorknob but not touching it, right? So the size of that lightning bolt that travels from John Travolta to the doorknob, right? The size of the induced current depends on the strength of a magnetic field, right? Where was the magnetic field in John Travolta? What magnetic field are we talking about? What was the little thing bouncing around inside of his body? Electrons. Electrons are negatively charged, so they are producing a magnetic field, right? So the magnetic field is covering the surface of his body. It's all these electrons covering the surface of his body, right? The velocity of a field as it cuts through the conductor. How quickly can electrons pass across the surface of the skin? It's pretty darn fast, right? But the faster they can pass, the more we would induce this flow of current, right? So the question is, if I induce the same static electric charge in a piece of copper versus John Travolta's body, where would the electrons travel faster? They would travel faster in the copper, right? So they would produce even that much more of a charge, which is the reason why if I shoot you with the taser's not made out of John Travolta. It's made out of copper, right? Because that metal conducts electricity better. It allows for more of an inductive velocity. The angle of the conductor to the magnetic field. He just got really weird, right? And the way he got weird was like twisted weird, right? He took the magnetic field and he's running it down a wire, so he's got it in the copper wire, and he started twisting the wire around, right? And if we go back to John Travolta, where was the static electric charge bunched up the most, right? In his hairstyle, right? Because his hairstyle's got those curls in it or whatever. So the same thing is true with that wire. We curve the wire around, and now we are bunching up this charge. We're allowing it to do that much more work, as it were. And the number of turns of the conductor is significant. The number of turns is going to be important. Why is it important? Well, because this is how transformers work, right? We've got two curves. We've got two coils. There's a primary and a secondary, right? And then we've got a space between them, right? And that space between them is the space in which the induction is occurring. It's the space between the finger and the doorknob, right? So we're inducing current across that space. The number of turns primary versus the number of turns secondary tells me what the voltage will be on either side, right? So if I know the voltage primary and the voltage secondary, I can figure out what the turns are and vice versa, right? So we will use this a lot, right? And if you're wondering how we use this, it goes back to that initial discussion of kVp versus mass, right? On the kilovoltage side, we've got what? Kilovoltage, right? So we need a transformer that steps things up. We'll have a step-up transformer that increases the voltage to kilovoltage. So it increases it to 10 to the third power. A lot, right? It goes from ones all the way up to 100s, right? Kilovoltage. So we're stepping up the potential difference a lot using a step-up transformer. Then with the mass, we have what? Milliamperage. So we're stepping down the current with a step-down transformer, right? Because we do not need all that many X-rays to be produced. We need a specified amount, and it's actually fairly small because an amp is like, was 6.3 times 10 to the 18 electrons per second, and we said that's like a gigazillion. We decided we don't need like a gigazillion, we just need like a zillion, right? So we stepped it down to milliamperage. So this is how we apply the transformer law every day that we're making X-rays. So it's there, it's embedded in the circuitry. We need to understand how it works in order to keep ourselves safe. The other thing that's important about this is all of this is happening on what we call the high voltage side of the X-ray tube, which should be encouraging to you, because what it means is as you're sitting there at the X-ray console drinking a Sprite or whatever kids these days drink, y'all are all still drinking Sprite, right? And you spill your Sprite, there you go, and you spill your Sprite on the console, are you going to be electrocuted with high voltage electricity? And the answer is no. But do you need to be drinking a Sprite around the X-ray tube? No, because it is high voltage, right? The X-ray tube has a high voltage circuitry running to it. If you look at the wires running to the tube, they're huge, right? Versus the wire that plugs the console into the outlet is just a standard wire. So something's happening between the console and the X-ray tube to produce a tremendous amount of electricity. So I want us to be aware of that.